Hello, my name is Stephen Hill and I'm recording this in Denver, Colorado. I'd like to welcome everyone to my talk today. I'm pretty excited to share what I've been doing with all of you who are listening and watching. And I'm looking forward to discussing these results and information here with you at the live sessions. So basically, we'll jump right into this. My work has been looking at Jupiter in a new light, so to speak, in the optical ammonia absorption band at 645 nanometers. And as far as I've been able to tell, this hasn't been done too extensively either in the professional or the amateur world. So let's jump in. The outline I'll cover today, I'll give an introduction, and then I'll talk about the observations that I've made, some photometry of Jupiter, that is disk integrated photometry. We'll look at meridional profiles of Jupiter, and we'll look for discrete features in ammonia, and then I'll kind of summarize and wrap up. The overall goal, though, of this presentation is to demonstrate the success of a fairly simple optical filter ratio method to observe Jovian ammonia. And the approach, as you can kind of see from the outline, is to progress from a simple global detection of ammonia to observations of discrete features in Jupiter's atmosphere in ammonia. So first, we'll look at some of the concepts here. Jupiter's atmosphere has two primary condensable cycles. One is based on water and the other on ammonia. And basically, you can't see the water clouds because the ammonia clouds are higher up than the water clouds, and they cover up the water clouds. The ammonia clouds are responsible for almost all of the banding and the features and beauty that we see when we look at Jupiter. The ammonia distribution that we're going to be looking at depends on vertical and horizontal motions in the atmosphere, so the winds, the updrafts, the downdrafts, as well as the sources of ammonia, that's chemical production and evaporating condensates, as well as the sinks, where ammonia disappears to, where it goes away, condensation and photochemical destruction. So basically, what we're saying is that the ammonia at the upper levels of the atmosphere plays the same role as water does in Earth's atmosphere in terms of clouds and weather. Ammonia is kind of a proxy for active weather in the upper troposphere. Now, if you look at the figure on the right here, we've got visible light images of Jupiter and then contemporaneous retrieval of ammonia density at about the 500 millibar level from some sophisticated professional equipment from Fletcher et al. In 2016. What you can see is that there is some association of features with the optical. So you can see a lot of depletion, that low blue color in the ammonia. Right here near the north equatorial belt, and then you've got some enhancement below that in the equatorial zone. The red spot, you've also got kind of this hollow around where there's a depletion in ammonia. So you can see some general correlation, but it's not precise. And just to highlight that, here's where the red spot is outlined in the yellow. And you can see it's not actually in the middle of that depletion zone. There's kind of at the upper edge, and there's a little central enhancement. So it goes to show you that the visible light images we see in color do not always correspond to the kinds of things we see with ammonia enhancement. So what are we looking for in the ammonia signal? Both ammonia and methane have molecular absorption bands in the visible and near infrared. The methane bands are strong, and they're a standard part of both professional and amateur astronomers' toolkits for many, many years now. But amateurs have been taking pictures in the methane band at 889 nanometers for quite a number of years now. Ammonia bands, however, are weak and have been less explored, although there has been some spectroscopic and some imaging spectrometry done. And to give you an idea of the differences in strength, here's that big methane band that we like to take pictures of Jupiter in. Here's the ammonia band that I'm going to be working with. So what's the technique? The technique is to look at the absorption band in a narrowband filter at 647 nanometers, that's the closest I could come to the exact 645 nanometers of the ammonia band, and then compare that band, the signals in adjacent continuum bands. So 656 or 658 or 672, these are common bands that are used in astronomy. The 647 band had to be procured from Edmund Optical. And the only difference between those bands should be the absorption of the ammonia. And you can see that right there, where we've taken the signal up here. The red line shows the actual albedo of Jupiter. The blue line is a fit across the absorption band, so it represents kind of a quasi-continuum if there wasn't this absorbing gas there. And if you run both of those through the filter, the 647 filter, and actually the other filters, you see there's a difference right there in the 647 filter at the top there. It's a few percent, but there's no difference in the other filters. So the equipment we used, it was a Celestron 11 0.28 meter telescope. As I said, I'm in Denver, Colorado, and you've got a listing there of the filters used, as well as the software used for analysis. Some custom Python was developed. And then you've got two main sets of observations. I used a CMOS camera in a Lucky imaging mode at a long focal length that was basically non-quantitative. It's an uncooled camera. And those are those first observations in July that you see in the top table. And then the second set of observations are using a CCD at a larger plate scale, so less detail. And that's a series of 11 observations in September and October. So how does this work? What we want to look at is the equation at the top here. I'll go through these really quickly. The signal we see is basically the integral of the solar flux times the albedo of the object we're looking at, times the transmission of the Earth's atmosphere, times the response of the instrument. And then I've pulled out the filter that we're using separately. All of those are functions of wavelength, and we integrate over them. But the flux of the sun, the transmission of the atmosphere, and the response to the instrument should be relatively constant over time and are relatively smooth in wavelength. So we can approximate them by averages and pull them out of the integral. What we want to look for is we want to look for the signal we're expecting in Jupiter with and without the ammonia. So if you figured you could predict what Jupiter would look like if it had no ammonia, you could do this by using the moons of Jupiter to estimate what the ratio of continuum signal would be between 647 and say 656 nanometers. Multiply that by the signal at Jupiter at 656 nanometers, and you'd get the hypothetical 647 ammonia-free signal. Now, what you actually see, of course, is Jupiter with the ammonia absorption at 647, and that's simply the product of that hypothetical continuum signal with the transmission of ammonia in Jupiter's atmosphere. We can go one step further, and we can go back to that other slide where I showed that small deficit that you see in the signal in 647 that's due to ammonia. You can let these terms cancel out. All you have to do is integrate the albedo of Jupiter with and without ammonia absorption and the 647 filter there, and you find that you get a signal of about 0.96 in terms of the transmission, which means our ammonia absorption is about 0.0387, about 3.8%. Now, what do the results look like when we actually look at Jupiter? Well, we get an absorption of about 0.024 with an error bar that's about 0.016. I claim that's a poor agreement, and that was much less than I had hoped for. So I look at two different issues here. The first one is the fact that there were poor observing conditions from the 24th of September through the 9th of October. Living in Denver, Colorado, there were major wildfires right here in the Rockies. And depending on wind conditions, we got very thick smoke to sometimes moderate smoke. And I started rating the observing conditions in late September as having moderate smoke. And moderate by that rating was basically you could see visible reddening in the sky of astronomical objects. Certainly the magnitudes were shut down quite a bit. And what you see here in this plot, these are all the 647 over 656 nanometer filter ratios for every image of Jupiter and moons. And you can see that in the latter half there, those last 5 observations, there's a lot more scatter, there's a lot more variability, and that shows up in the statistics as well. The second thing to look at is Jupiter's Galilean satellites have continuum color slopes, and they show temporal variations due to rotation. Now, you can see this kind of subtly here at this scale in the top chart, where you've got these slopes that in the 640 to 660 range, they are non-zero. And if you look at the slope of Jupiter's albedo in that range, it is pretty darn flat. This leads you to see things like this, where you can see different moon slopes compared to what you get in a ratio from 656. You can see differences there that show up and look like an ammonia deficit in Jupiter, except it looks like you're getting an ammonia deficit on the Galilean moons just because they have this slope. So those are two things to take care of and look at. So I explored the data along 3 dimensions, either including or excluding dates, taking corrections for the moon color slopes, and also I chose to include or disinclude Io because Io shows the largest rotational variability in color slope. So what you can see is in this table, the columns show uncorrected and corrected for the moon slopes here. We were able to add in those couple % changes that you would expect from the moons because they have a slope and Jupiter doesn't in terms of their color continuum. And then you can see the dates here, September 2 through the October 9th. That's all of the dates with and without Io. And then for September 2 to 15, that's the first set of 6 dates that have the lower scatter, both with and without Io. And then finally, the last dates here. And what we see pretty clearly is that if you look at the data in the first half of September, we get much better results. We get results that have about a plus or minus 20% accuracy, and this O minus P column, that's observed minus predicted, is showing errors in the maybe 10 to 12% range. So that's much better than we had originally. And you can look at the bottom rows here when we just look at the last dates, and you can see that we have much, much larger values of uncertainty, 0.24. It's basically the same magnitude or even larger than the measurement we're making. So we're discrediting those, and we're claiming that these are the accurate measurements in that first half of September, corrected for the moon color slopes. Let's move on and look at profiles and maps. So what I did here was I stacked maps of Jupiter from basically 45 degrees on either side in longitude and either side in latitude from the sub-Earth point on Jupiter. I did not pay attention to the exact longitude, so these are kind of smeared maps. They smear in longitude and they emphasize latitude differences. You can see the panel descriptions at the lower left, and these are from 2 different sets of dates. There's the CMOS observations from July, which are all averaged together, and then there's the first half of September observations with the CCD. Now, on the center panel to the right of each of these frames is the ammonia absorption or the ammonia abundance maps. And what you see there is a lack of correlation directly with a lot of the other features. You see some correlation, but not a huge correlation. The biggest thing I want to point out is this right here, which is the equatorial zone enhancement, which is a well-known feature that's been around for a long time, discovered quite a while ago in ammonia. So we're seeing this persistent feature. It's not associated with continuum slope or reflectivity or these other sorts of things that we have in these context images. Now we can go and actually compare these profiles to professional work done by Fletcher et al. In 2016 using the Texas instrument on the IRTF telescope and Cassini-Sears data. Those are the values that are in red and black. And then in green, purple, and blue, you can see data from my work. Basically, the total sum of the data averaged there from July 20 to September 15th, not including those last bad days in September and October, is shown in the blue curve. And you can see we reproduce the main features such as the equatorial zone enhancement over here, maybe a little bit more positive north of the equator. You can see there's also some differences here, particularly around the south equatorial belt and a little bit around the north equatorial belt. We see more ammonia enhancement than was seen in these two other data sets, which are from 2000 and 2014. So let's look at discrete features. Again, we've got the same layout of plots here. I've got the ammonia enhancement chart highlighted in yellow. This is a lucky imaging sample from July 29th. What you can see is we've got this enhancement around the northern edge of the equatorial zone, right at the bottom of sort of these dark features that we often see kind of dangling down into the equatorial zone from the north equatorial belt. And you can see these enhancements right here. And it's very interesting because they do not directly correlate to things that you might see in the visible. They're close, but they aren't overlapping. For example, these darker areas, or actually redder areas here. Bluer areas are the dark ones. And of course, we've got the great red spot on here, which is going to be interesting. So now we'll look at some of the discrete features a little bit more closely. And first we'll look at the equatorial zone and the north equatorial belt. Here, these are the features that I showed in the previous slide, these enhancements just above the equator. And then you can see these bluer regions which correlate to the dark features in visible light. You can see those dark features here and here, and you can see kind of a bright plume here. You've got the methane image here and near ultraviolet image here. And the key thing to show is this lack of correlation and the fact that these things are occurring at different latitudes. If you look, you can see now, I've drawn this at about 6 degrees, you can see that the features that are bright in ammonia do not actually overlap with the dark features, at least not completely. They lie on the lower edge, they lie in the equatorial zone, and they partially overlap some of the bright plumes, as well as lying on the edge or overlapping a little bit with the dark features. And then in this next zoom, we see the equatorial zone south of the equator to the south equatorial belt, including the great red spot. And the really interesting thing here is just how dark the red spot is in reflectivity, which you can see up here in this chart, which is basically a monochromatic version of the color image over here, how bright it is in terms of how red it is. It's a very red feature. And then you've got it being, of course, bright in methane and dark in the NUV absorption, aerosol absorption. But what you don't see is a strong signal in ammonia. So you've got all these other drivers. It's dark, it's very red, it's bright in methane, and it's dark in NUV, and yet none of that is influencing the signal in ammonia, which really suggests that there is no, that the ammonia measurements are actually independent of all of these other things and are actually physical measurements. And just to show where the great red spot is, I've highlighted the locations on the different images there. So to wrap it up, basically I presented that a simple filter ratio method is demonstrated to detect ammonia on Jupiter. The approach should be accessible to amateur astronomers at a modest cost, and advanced amateur astronomers could provide regular observations and monitoring of ammonia distributions to the professional community. Got some detailed observations and findings on the right-hand side. But I do want to move on just to a couple of acknowledgements here. I want to thank Dr. John Rogers of the British Astronomical Society for some insightful correspondence and encouragement regarding this research. And I'd also like to thank several observers for the use of their publicly available color context images, which when I did not have my own, I borrowed from Alpha Japan. And then we have the bibliography. Thank you so much for watching this, and I really appreciate your attention and look forward to having a discussion with you about some of the results that I've presented here. Thank you.